Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be drifting into the vast and turbulent world of cyclones. Where oceans swirl and skies spiral, these godlike forces can wreak unimaginable destruction. These storms are not just wind and rain, but lifelike systems of immense motion and energy. They rise from clouds and grow into rotating structures bigger than the eye can see. From the surprising stillness at their center to the unimaginable forces that move them, they reveal the true power that nature can hold. As we journey through this world of wind and water, you may find yourself viewing weather in a whole new way. Not as something boring or abstract, but as something dynamic and deeply alive. There is a rhythm to these storms, a balance between chaos and order, and curious patterns that repeat throughout nature. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, there's nothing you need to do but relax. Allow yourself to get comfortable. Allow your mind to settle. And as the day begins to gently fade away, join me as we explore these remarkable forces of nature together. Let's begin. A cyclone is a giant spinning engine powered by warm ocean water. What makes that idea so astonishing is the scale. A storm does not burn fuel the way a machine does. Instead, it feeds on heat rising from the sea and moisture lifting into the air. As that vapor cools high above, it releases energy, and that energy helps the storm pull in more air, more moisture, and more warmth. It becomes a self-strengthening system, turning invisible ocean heat into wind, cloud, and towering rain. This is why tropical seas matter so much. They are not just the setting. They are the power source. When conditions line up, a patch of unsettled weather can begin acting like an enormous natural engine, drawing strength from water spread across hundreds of miles. Once you see that, a cyclone stops feeling like random bad weather and starts feeling like one of the planet's most extraordinary physical processes. The calm eye in the middle of the cyclone can feel eerily peaceful inside a storm built for chaos. That contrast is one of the strangest things in all weather. Around the center, the eye wall roars with the fiercest winds and the heaviest rain. Then, in the middle, air sinks instead of rising. Skies may brighten. Rain may stop. The wind may fade so suddenly that people step outside and think the danger has passed. In some storms, stars have even become visible overhead. That false peace has trapped many people through history, because the second half arrives soon after, with violent winds returning from the opposite direction. Roofs, already weakened by the first assault, can fail more easily when the storm comes back around. Trees that leaned one way can be pushed the other. The eye feels unreal, because it is. You are standing in the center of a rotating system that is still fully alive, still fully dangerous, and still carrying immense force all around you. Cyclones begin as clusters of thunderstorms, then grow into rotating worlds. That transformation is one of the great dramas of the atmosphere. At first, there may be nothing that looks especially legendary, only disorganized bursts of convection over warm water. Thunderstorms flare, collapse, and flare again. But if the surrounding environment is favorable, those storms start working together. Rising air lowers pressure near the surface. Air rushes inward to replace it. The Earth's rotation nudges that inflow into a spin. Little by little, a pattern emerges. Rainbands curve. The center tightens. The system begins to organize around a shared circulation instead of scattered bursts of weather. What feels so captivating is that the ingredients seem familiar. Thunder, clouds, rain, warm sea. Then the structure changes, and something much larger is born from those ordinary parts. A cyclone is not dropped onto the ocean from nowhere. It develops through stages, like a story gathering momentum, until a once chaotic cluster becomes a coherent and dangerous atmospheric world. Earth's spin quietly twists these storms into their famous spiral shape. Without the rotation of the planet, tropical cyclones as we know them would not take form. Air rushing toward low pressure would move inward, but it would not begin curving into the broad, organized swirl that gives the storm its identity. Because Earth turns, moving air is deflected to the right in the northern hemisphere and to the left in the southern. That subtle effect is enough to bend inflowing air around the center, building rotation that can tighten as the pressure falls. The result is the spiral pattern people recognize instantly in satellite images. This also explains why these storms do not form right at the equator, where that turning influence becomes too weak. It is a beautiful reminder that cyclones are not separate from the planet. They are shaped by the planet's motion itself. A storm at sea is not only interacting with water and air. It is also responding to the fact that Earth is spinning beneath it. One cyclone can release more energy than many nations use in days. That statement sounds exaggerated until you remember how much heat and moisture are involved. A large tropical system processes immense quantities of water vapor, and every time that vapor condenses into cloud and rain, energy is released. Added up across the whole storm, the total becomes staggering. Scientists often compare cyclone energy with human scales for that reason, not to be dramatic, but because ordinary weather language is too small for the reality. The important point is not that a cyclone behaves like a power plant. It does not deliver neatly usable electricity. The point is that the atmosphere can move and transform astonishing amounts of energy through natural processes alone. That is why these storms can sustain violent winds, deep convection, and broad circulation over long periods. They remind us that the Earth system operates on scales far beyond daily experience. What seems like a bad storm from the shoreline is, in physical terms, an immense release of stored planetary heat. Cyclones can rearrange coastlines in a single night with wind and surge. Few natural events can reshape the edge of the land so quickly. When a strong storm drives seawater ashore, beaches can be stripped away, dunes can be cut open, and whole inlets can appear where none existed before. Sandbars shift, barrier islands migrate. Roads that sat comfortably inland can wake up exposed to open water. In some places, salt water rushes across fields and marshes, leaving behind a changed landscape long after the clouds have gone. Wind adds another layer of force by toppling trees, tearing apart coastal forests, and hurling debris into places that once seemed sheltered. After major landfalls, maps sometimes need updating because shorelines no longer match what was there before. That is part of what makes these storms so compelling. They do not merely pass over scenery. They can edit the boundary between sea and land, proving that even a familiar coast is never as permanent as it appears. These storms are so vast that satellites see them swallowing whole seas. From the ground, people experience rain, wind, and darkness. From space, the view becomes almost unbelievable. A mature cyclone can spread cloud bands across an area larger than many countries, with curved arms wrapping around a center that looks organized on a planetary scale. Satellites reveal the full architecture at once, from the dense central overcast to the far outer bands that sweep over distant waters. That perspective changed meteorology forever, because before space-age observing, no one could routinely see the entire storm in a single view. Now forecasters can watch it breathe, tighten, wobble, and evolve hour by hour. The sight is mesmerizing because it makes the atmosphere look alive. A cyclone does not resemble a random blot of weather. It resembles structure, motion, and intent spread across the ocean. Seen from orbit, the storm becomes both more beautiful and more humbling, because its true size finally comes into focus. A cyclone can pull heat from the ocean like a planet-sized battery. The comparison works because warm water stores energy that the atmosphere can tap when the right pattern begins. Sunlight has been heating the upper ocean for weeks or months. Then a storm arrives and starts drawing moisture upward. Each parcel of rising air carries hidden heat with it, and when that moisture condenses into cloud and rain, energy is released into the storm's core. That helps the pressure fall, and the winds tighten further. It is a remarkable exchange between sea and sky. The ocean gives up part of its stored warmth, and the storm converts it into motion on a colossal scale. Afterward, the water beneath may actually be cooler because the cyclone has stirred the surface and spent part of that heat reserve. This is one reason these systems feel so dramatic to study. They show that energy can sit quietly in the environment, then suddenly emerge as one of Earth's most powerful moving phenomena. The deadliest part is often the sea, not the screaming wind. That surprises many people because wind is what looks most dramatic on television. Trees bend, signs tear free, roof panels fly. Yet water is often the true killer. Storm surge pushes the ocean inland with relentless force, filling streets, homes, and escape routes far faster than many people expect. Waves ride on top of that surge and smash buildings already standing in water. Boats become battering rams. Cars float, stall, and vanish. Even the person who survives the wind can be trapped by rising water in darkness. History is full of storms remembered not for the highest gusts, but for the wall of sea that arrived with them. In low-lying places, elevation can matter more than distance from the shore. That is why evacuation orders are so urgent. They are often less about hiding from wind and more about getting out of the path of moving water, which is heavier, less forgiving, and terrifyingly efficient at taking control. Even after landfall, a cyclone can keep flooding regions far inland. Many people imagine the main danger ending once the center crosses the coast, but the storm's moisture can travel much farther than its ocean power source. As the system moves inland, it may weaken in wind, yet it can still carry enormous amounts of tropical rain into river basins, valleys, and mountain slopes. The result is often prolonged flooding far from beaches and harbors. Creeks rise into torrents. Rivers crest days later. Roads disappear under brown water where no one expected a coastal disaster to reach. In some cases, saturated ground gives way and triggers landslides. This inland threat has shaped some of the most costly and deadly cyclone disasters on record, because people who live far from the shore may feel falsely protected by distance. The storm changes character rather than vanishing. Its violence shifts from surge and coastal destruction toward rain, runoff, and swollen waterways, extending the story far beyond the moment of landfall. Cyclone, hurricane, and typhoon are different names for the same storm. That surprises people because the words feel as if they belong to different kinds of weather, yet the storm itself follows the same basic design. The name changes with geography. In the Atlantic and the eastern North Pacific, people say hurricane. In the western North Pacific, they say typhoon. Around the Indian Ocean and the South Pacific, cyclone is the usual word. What changes is language and region, not the core phenomenon. That makes these storms feel strangely universal. Communities thousands of miles apart have watched the same spinning force approach their shores, and given it a local name shaped by history, trade, and culture. One planet, one kind of storm, many human traditions. It is a reminder that weather is global even when our words are regional. The map divides the names, but the atmosphere does not. The same ocean-fed engine keeps appearing under different titles wherever warm seas and turning air allow it. Cyclones cannot form right on the equator because the spin is too weak. This sounds almost unbelievable because the equator is warm, humid, and stormy. It seems like the perfect birthplace. Yet one essential ingredient is missing. Near the equator, the deflecting effect created by Earth's rotation becomes so small that air rushing inward cannot organize into a proper tropical spin. Thunderstorms can still explode there. Torrential rain can still fall. But the atmosphere struggles to gather that activity into the closed, rotating structure a cyclone needs. Move a little farther north or south, and the odds improve. That is why most tropical systems are born several degrees away from the equator rather than directly on it. It is one of those rules of the planet that feels hidden until you learn it. The warmest waters alone are not enough. A cyclone needs a turning Earth in just the right way, and right at the middle line of the globe, that invisible twist is simply too faint. In the northern hemisphere, cyclones spin counterclockwise around their low-pressure core. Once you know that pattern, satellite images start to feel easier to read, almost like learning a new alphabet of the sky. Air flows inward toward lower pressure, but it does not move in a straight line. Because of Earth's rotation, the path bends to the right as the air travels. Around a tropical low, that constant deflection produces the familiar counterclockwise circulation. It is not a decorative flourish in the cloud pattern. It is the signature of the forces shaping the storm from moment to moment. This also explains why the strongest weather wraps around the center instead of simply rushing toward it and stopping there. The whole system is an organized dance between inflow, rotation, rising motion, and release aloft. For someone watching from space, the direction becomes instantly recognizable. For someone living beneath the clouds, it helps determine which side delivers stronger onshore winds, rougher seas, and the most dangerous arrangement of hazards. In the southern hemisphere, cyclones spin clockwise for the very same reason. The storm does not reverse because it becomes a different creature. It reverses because the underlying deflection reverses. South of the equator, moving air is bent to the left instead of to the right. That one change is enough to flip the entire circulation. The result is a mirror image of the storms seen in the north, with the same low-pressure center and the same broad spiral form, but turning the opposite way. There is something elegant about that symmetry. One planet produces two versions of the same atmospheric structure, each faithful to the hemisphere where it forms. For meteorologists, the turning direction is basic knowledge. For everyone else, it can feel like a secret built into the geometry of Earth itself. Even the cloud bands tell you where the storm was born. Look long enough, and you begin to see that a cyclone is not only weather. It is geography, rotation, and physics written together in motion. Every cyclone begins with rising air and pressure dropping at the surface. That is the quiet opening move behind every dramatic landfall and every famous satellite image. Air near the surface warms, moistens, and begins to rise through deep convection. As that air ascends, there is less mass pressing down on the surface below, so pressure starts to fall. That drop matters because air naturally moves from higher pressure toward lower pressure. The atmosphere begins feeding the growing disturbance, sending more air inward near the surface where it can rise and turn. Bit by bit, a feedback takes hold. Rising motion encourages lower pressure. Lower pressure encourages inflow. Inflow helps sustain more rising motion. It is a beautifully simple idea that scales into something enormous. Before the roaring wind, before the eye, before the warnings and the maps, the storm begins with a vertical rearrangement of air and weight. A cyclone is born when the atmosphere starts lifting strongly enough to change the balance at the surface beneath it. Warm water, moist air, and weak wind shear give cyclones their chance. Think of those ingredients as permission rather than guarantee. Warm water loads the lower atmosphere with heat and evaporation. Moist air helps thunderstorms keep building instead of choking on dry intrusions. Weak wind shear allows the developing system to stand upright, so the circulation near the surface stays connected to the thunderstorm towers above. Remove any one of these, and the storm may struggle or fail. Keep them together long enough, and the disturbance has room to organize. That is why some tropical waves cross an ocean and never become memorable, while others suddenly gather structure and command the attention of entire coastlines. The environment is deciding whether the atmosphere can stack itself into a coherent engine. When people hear that a storm has entered favorable conditions, this is what forecasters mean. The sky and sea are aligning in a way that makes growth possible. The storm still has work to do, but the door has opened. Most tropical cyclones need sea temperatures above about 26 degrees Celsius. That threshold is not a magic switch, but it is a useful clue to where these storms are most likely to thrive. Water that warm can supply the atmosphere with the evaporation needed to support persistent deep convection. Below that range, thunderstorms may still form, but the ocean usually does not provide enough sustained energy for a full tropical cyclone to mature and hold itself together. What makes this so interesting is that forecasters are not just watching the sky. They are studying the skin of the sea, searching for regions warm enough to support something much larger. It turns ocean maps into storm maps before the storm even exists. Yet the number alone is never the whole story. A warm patch of water still needs the right surrounding winds and the right atmospheric moisture. Even so, that temperature guideline has become one of the clearest signals that a stretch of ocean is capable of feeding one of nature's great spinning systems. A tropical depression is the quiet first step towards something much stronger. At that stage, the system has a closed circulation and organized thunderstorms, but its winds remain below the threshold for a named tropical storm. To the casual observer, it may not sound impressive. The phrase itself feels almost timid. Yet this is often the moment when meteorologists begin watching most closely, because the basic structure has formed. The atmosphere has crossed from scattered unrest into a defined, rotating entity. From here, the future can split in several directions. Some depressions fizzle quickly. Some wander over cooler water or into hostile winds and fall apart. Others take advantage of favorable conditions and intensify step by step into storms that later become unforgettable names in history. That is what makes the early stage so fascinating. It is the point where possibility hangs in the balance. A tropical depression is the first clear sign that the ocean and atmosphere may be starting a story much larger than their opening chapter suggests. Meteorologists track cyclones by measuring wind speed, pressure, and cloud structure. Those three clues reveal different parts of the storm's personality. Wind speed tells forecasters how intense the system is at the surface and how damaging it may become. Pressure gives a sense of how strongly the atmosphere has hollowed out at the center, which often relates to how tightly organized the storm has grown. Cloud structure shows whether the circulation is becoming more symmetrical, whether deep convection is wrapping around the core, and whether an eye may be trying to form. None of these signs tells the full story alone. Together, they help build a moving portrait of the storm as it changes from hour to hour. That portrait comes from many tools, including satellites, radar, ocean buoys, ships, and aircraft reconnaissance in some basins. Forecasting is not only about where the storm goes next, it is also about reading the storm's internal state. Meteorologists are watching a living system reveal its intentions through measurable signs. The eye wall is the fiercest ring, where the storm does its worst. This is the zone surrounding the eye, and it is where the strongest winds and the most violent upward motion are usually packed together. The thunderstorms here are not ordinary towers. They form a near-continuous ring of deep convection wrapped tightly around the center, and within that ring, the atmosphere is working at maximum force. Rain slashes sideways. Gusts rise to their peak. Pressure changes sharply over short distances. If the eye is the strange center of calm, the eye wall is the fortress that guards it. Crossing into it means entering the most punishing part of the cyclone. In the strongest storms, entire neighborhoods can experience a world of difference depending on whether the eye wall passes directly overhead or remains just offshore. That narrow shift in track can decide whether damage is serious or catastrophic. It is one of the clearest reminders that inside a cyclone, the most dangerous place is not the center itself, but the ring around it. The tallest thunderclouds in cyclones can tower higher than commercial airplanes fly. Inside the strongest parts of these storms, rising air can build thunderclouds to astonishing heights. Some tops push so far upward that they reach levels above the cruising altitude of many passenger jets. That means the storm is not only sprawling across the ocean, it is also reaching deep into the atmosphere, building vertical mountains of cloud from warm sea air below. In these towers, water vapor rises, condenses, freezes, and churns through violent updrafts that can carry droplets and ice high into the sky before gravity drags them back down. Lightning can flash within these walls of cloud, though tropical cyclones are often less electrically active near the very center than ordinary thunderstorms inland. Even so, the scale feels almost unreal. A person on the ground sees only rain and darkness. Above, the storm has built a stacked architecture so tall that it rivals the flight paths of machines designed to cross continents. Spiral rain bands can stretch far from the center like moving arms of weather. Long before the core arrives, these sweeping bands can begin changing the world beneath them. They arc inward across the sea and land, carrying bursts of heavy rain, sudden wind, and an unsettling rhythm of arrival and pause. One band passes, and conditions ease. Another follows, and the storm seems to lean closer. That pulsing structure is part of what makes a cyclone feel alive. It does not hit everywhere at once. It reaches outward in curved lanes of weather that can extend astonishing distances from the center. Within them, squalls may rotate around the storm for hours, delivering pockets of intense rain and gusts strong enough to tear branches loose or flood streets before the eye is anywhere nearby. For coastal communities, these outer bands are often the first real sign that the atmosphere has changed character. The sky no longer feels like ordinary bad weather. It feels organized, rotating, and increasingly committed to arrival. The eye forms because sinking air clears clouds at the storm's center. That clearing happens because the storm's fiercest upward motion is concentrated in the ring around the center rather than in the center itself. As air rises violently in that surrounding wall of thunderstorms, some of it spreads outward aloft, while some begins to sink in the middle. Sinking air warms as it descends, and warming air discourages cloud formation. Little by little, the central region dries and clears compared with the chaos around it. What emerges is one of weather's strangest structures, a relatively calm hole inside a system built from deep convection and intense rotation. The stronger and more organized the storm becomes, the more clearly this central feature can develop. In satellite images, That clearing can look almost deliberate, like a pupil opening in the middle of the cloud mass. It is a beautiful example of order arising from violence, where the very processes that make the storm ferocious also carve out its most famous hollow. Some eyes are tiny and pinched, which can signal a dangerously intense cyclone. Meteorologists sometimes call these pinhole eyes, and their small size can be a clue that the storm's core has become tightly wound and extremely efficient. When the central region contracts, the ring of strongest winds may pack closer to the middle, creating a compact engine with exceptional intensity. From space, the feature can look almost too neat to be real, a tiny, clear dot surrounded by a dense ring of towering cloud. That visual can be deceptive, because small does not mean mild. In fact, some of the most violent tropical cyclones have displayed very small eyes at their peak. For people in the storm's path, a compact system can also create steep changes in conditions over short distances. One place may experience catastrophic wind, while another nearby escapes the worst. That sharp contrast makes these storms especially unsettling. Their scale may appear modest on a map, yet their inner core can be frighteningly powerful. An eye wall replacement can briefly weaken a cyclone before it grows wider. In very intense storms, a second ring of thunderstorms can sometimes form outside the original core. When that happens, the inner ring may begin to fade, while the outer ring strengthens and takes over. During that transition, the storm often loses some peak wind speed, which can make it seem as though it is easing. But the story is more complicated than simple weakening. As the outer ring becomes dominant, the wind field can spread outward, so the area affected by damaging conditions may actually expand even while the top winds dip. For forecasters, this is one of the most fascinating structural changes a cyclone can undergo, because it shows the storm reorganizing itself in real time. For people in its path, it can be deeply confusing. A storm that looks weaker on paper may be growing broader and still very dangerous. The cyclone is not surrendering. It is changing shape, redistributing power, and preparing a different kind of threat. Cyclones breathe through outflow high above, venting air into the upper atmosphere. Near the surface, air spirals inward. Near the top of the storm, that air must go somewhere after rising through the thunderstorm core. It spreads outward, fanning away from the center in all directions when conditions are favorable. This hill-level exhaust is called outflow, and without it, the storm would have trouble sustaining its structure. You can think of it as the atmosphere's pressure release system. The cyclone draws air in low, lifts it through deep convection, and then lets it escape aloft so more air can keep entering below. In satellite images, strong outflow can create delicate cirrus plumes that stream away from the storm like feathers or veils. Those wispy tops are signs of a healthy upper-level release, and they often appear around well-organized systems. The idea is mesmerizing because it makes the storm feel almost biological. It inhales at the ocean surface, exhales near the top of the troposphere, and survives by keeping that circulation open. Without that upper escape route, many storms choke before they fully organize. A developing cyclone cannot keep piling air upward forever. If the rising motion has nowhere to spread out, the whole system begins to jam itself. Pressure does not fall as effectively. Thunderstorms become less coherent. The circulation struggles to tighten into a mature, self-sustaining core. This is why the upper atmosphere matters so much, even though the storm draws its energy from the ocean below. A tropical disturbance may have warm water beneath it and abundant moisture around it, yet still fail because the air aloft is not arranged in a helpful way. Forecasters pay close attention to this invisible architecture. They are not only asking whether the sea is warm enough. They are asking whether the sky above will allow the storm to ventilate. That idea gives cyclones an added layer of fascination. They are not simply stacks of weather. They are vertical systems that must work from the ocean surface to high altitude, or the whole attempt can collapse. Dry air can invade a cyclone and unravel its structure from within. Tropical systems thrive on moist, rising air, so pockets of dry air are deeply disruptive when they slip into the circulation. Once drawn inward, that drier air can weaken thunderstorms, reduce the release of latent heat, and break apart the symmetry the storm needs to stay organized. Parts of the core may erode. Convection may flare on one side and collapse on another. Satellite images can show ragged gaps where a cleaner, stronger storm would have solid cloud cover. This intrusion is especially damaging because it attacks the storm from the inside rather than striking it from outside like a wall of hostile wind. A cyclone can look impressive from a distance, yet be quietly struggling with internal dryness that prevents it from consolidating. That makes dry air one of the atmosphere's most effective saboteurs. The ocean may be warm, the spin may exist, and the clouds may appear dramatic, but without enough moisture in the right places, the storm can begin to hollow out. Strong vertical wind shear can tilt a cyclone and tear it apart. This happens when winds change significantly with height, pushing the top of the storm in a different direction from the lower circulation. A healthy tropical cyclone prefers to stand upright, with its center stacked through the depth of the atmosphere. When strong shear arrives, that vertical alignment can be disrupted. Thunderstorms get displaced away from the low-level center. The storm starts looking lopsided. The deep convection that should be wrapped around the middle ends up shoved to one side, leaving the circulation exposed and vulnerable. In severe cases, the system can be pulled apart so thoroughly that development stops altogether. It is an elegant reminder that a cyclone is not only about strength, but balance. The storm must keep its tower of motion aligned from bottom to top. Once that balance is lost, even a promising system can quickly look sickly. A cyclone may have power available, but shear determines whether it can keep its structure long enough to use it. Warm ocean currents can help a storm intensify with shocking speed. Not all warm water is equal. A storm passing over a broad, deep current of unusually warm water can find a much richer energy source than it would over a shallower warm patch. In those places, the cyclone's own churning does less to cool the surface, so the ocean keeps feeding heat and moisture into the storm instead of being exhausted right away. That is one reason certain currents have earned a fearsome reputation in forecasting. They can act like hidden accelerators beneath the sea, turning a strengthening storm into a suddenly much more dangerous one. When that happens near land, the consequences can be severe because communities have little time to adjust to the new threat. Rapid intensification feels dramatic because it reveals how sensitive cyclones are to what lies below them. The surface may look like open water to the human eye, but underneath, the storm may be crossing a river of stored heat, powerful enough to transform its future in hours. Rapid intensification can turn an ordinary storm into a major threat overnight. One evening, a storm may sound manageable, a system to watch, a concern for later. By the next morning, it can be something far more serious, with winds sharply stronger and the window for preparation suddenly smaller. That is what makes rapid intensification so unsettling. It compresses time. A cyclone that seemed ordinary can find an ideal pocket of warm water, moist air, and favorable upper winds, then reorganize with startling speed. The inner core tightens. Thunderstorms wrap more completely around the center. Pressure falls quickly, and the storm begins climbing the scale before many people have emotionally caught up. This is not only a forecasting challenge. It is a human challenge, because people often prepare in stages. Rapid intensification interrupts that instinct. It turns hesitation into danger. In the space of a single night, maps, warnings, and expectations can all shift, reminding us that some of the most dramatic changes in weather happen while most people are asleep. Some cyclones strengthen so fast that forecasts struggle to keep pace. Forecasting has improved enormously, yet storm intensity still contains some of the atmosphere's most stubborn surprises. A cyclone can look healthy but not exceptional, then suddenly sharpen into a much more powerful system in just a few hours. That speed matters because official forecasts are built from observations, model guidance, and update cycles, while the storm is changing continuously over open water. By the time one advisory reaches the public, the cyclone may already be partway into a new state. This is not carelessness. It is a sign of how many finer-scale processes must align inside the core before explosive strengthening appears. Tiny structural shifts can have huge consequences. That reality gives tropical forecasting a strange tension. We can often predict the path with growing confidence, yet the storm's personality may still transform faster than expected. The result is a race between observation and evolution, with meteorologists trying to describe a system that is rewriting itself in real time. Storm surge is seawater pushed ashore, and it drowns cities with speed. This is not a single towering wave crashing dramatically and then disappearing. It is the ocean itself moving inland under the force of sustained wind, rising into streets, buildings, and neighborhoods that were never meant to hold it. Once that water starts advancing, it can spread with frightening speed across low ground, lifting vehicles, breaching doors, and cutting off escape routes. In some historic disasters, entire communities were overwhelmed before many residents fully understood what was happening. That is part of what makes storm surge so terrifying. It turns familiar places into seabed. Street grids vanish under moving salt water. Landmarks that once seemed permanent become reference points in a temporary bay. And because the water is driven by a vast rotating storm, it can keep piling higher for hours. Wind may grab headlines, but surge changes geography in a far more intimate way. It enters homes, climbs stairways, and makes the ground itself feel unreliable. A modest cyclone at high tide can become far deadlier than expected. Timing matters in coastal disasters, and the tide is one of the quiet reasons why similar storms can produce very different outcomes. A cyclone that arrives near low tide may still be dangerous, yet one that pushes water ashore when the sea is already elevated can start from a much worse position. The ocean does not need to climb as far before it spills into vulnerable land. Defenses are overtopped sooner. Marshes and seawalls lose part of their margin. Roads flood earlier, and evacuation routes can fail while the storm is still approaching. This is why impact cannot be judged by wind speed alone. Two storms with similar strength may not behave alike when they meet the coastline. The clock matters. A high tide can turn a moderate event into a deadly one by giving surge a higher platform from the very beginning. That hidden alignment between storm and shoreline is one reason coastal forecasting demands such careful attention to local detail. Low pressure slightly lifts the sea, but wind does most surge damage. Many people imagine the ocean rising mainly because the storm's center has very low pressure, as if the sea is being pulled upward from beneath. That effect is real, but it is only part of the story, and not the dominant part. The larger force comes from wind blowing persistently across the water and driving it toward the coast. Over many hours, that push can heap enormous volumes of seawater against the shoreline, especially in shallow regions where the water has nowhere easy to go except inland. The pressure contribution is more like an added boost than the main engine. This is a fascinating example of how the atmosphere and ocean interact. The storm does not merely hover above the sea. It physically moves the sea through friction and momentum transfer. When the wind keeps pressing in the same direction, the ocean responds. Surge becomes not just a rise in water level, but a mass relocation of water by air. Coastal shape can amplify storm surge like a funnel, magnifying a wave. Not every shoreline receives rising water in the same way. Some coasts are broad and open, while others narrow into bays, inlets, estuaries, or river mouths that can concentrate incoming water into a smaller space. When the cyclone pushes the sea toward one of these shapes, the coastline can act like a funnel, forcing more water into less room and raising levels higher than a simple open coast might experience. This is why geography can turn one location into a hotspot of danger while another nearby sees much less flooding. The form of the land and the layout of the seabed are shaping the disaster as surely as the storm itself. A curved bay, a narrowing channel, or an estuary aimed the wrong way can intensify what arrives. That makes storm surge feel less like a generic threat and more like a conversation between weather and place. The coastline answers the storm according to its own shape. Shallow continental shelves often make cyclone surges much more dangerous. Where the ocean floor rises gradually toward land, incoming storm-driven water can pile up more efficiently than it does along coasts where the seabed drops off steeply. Over a shallow shelf, the wind is pushing against a broad expanse of relatively thin water, and that setup allows the sea level to build higher as it is forced shoreward. It is one of those hidden features that most people never see, yet it can strongly influence how catastrophic a landfall becomes. The danger is not only in the storm overhead, it is also in the underwater landscape beneath it. Two coastlines may look similar from the beach, but one may sit beside a seabed that makes surge far worse. This gives cyclone impacts an eerie geological dimension. The contours laid down over ancient time can determine the violence of a modern storm. A shallow shelf is like a quiet accomplice, invisible from shore, yet crucial in deciding how far the sea can invade. Freshwater flooding kills many people long after the eye has passed. After the drama of landfall, many assume the story is ending. In reality, another chapter may be beginning across rivers, creeks, and floodplains far from the coast. Tropical rain can continue draining through landscapes for days, collecting in channels that rise long after the strongest winds have faded. A road that looked safe at dusk can be underwater by dawn. A river that seemed contained can spill outward with astonishing force as runoff from distant hills finally arrives. This delayed danger catches people because it feels less cinematic than landfall. There is no swirling eye overhead, no famous satellite image, only brown water creeping higher, bridges disappearing, and currents strong enough to sweep away vehicles and people. The threat lingers after the headlines move on. In some communities, the worst losses come when residents think the crisis has passed and try to return, travel, or clean up. Water keeps rewriting the ending after the storm's center is gone. Mountains can wring torrents from cyclone clouds and trigger catastrophic landslides. When a moisture-laden cyclone meets high terrain, the landscape itself forces the air to rise even more. That extra lift squeezes out enormous rainfall, sometimes on slopes and valleys that are poorly equipped to absorb it. Hillsides become saturated. Streams leap their banks. Soil loosens around roots and rock, and whole sections of ground can suddenly give way. This process can turn a storm that was weakening in wind into a severe mountain disaster, with flash floods racing through ravines and landslides burying roads, villages, and farms. In some regions, this is among the storm's most lethal transformations. The cyclone arrives from the sea, but the mountains alter its final character. They convert tropical moisture into concentrated downpours with devastating efficiency. It is a powerful reminder that the danger of a storm is never only in the clouds themselves. The shape of the land decides what that moisture becomes once it arrives, and steep country can make it deadly. Cyclones can spawn tornadoes, especially after they move inland. This surprises many people because a cyclone already feels like more than enough storm for one system to contain. Yet within its outer rain bands and changing wind fields, smaller rotating storms can develop, and some of those rotations tighten into tornadoes. These tornadoes are often not the enormous long track monsters seen on the plains, but they can still be destructive, fast-forming, and difficult to warn for, especially when embedded in heavy rain. The danger tends to increase after landfall because the storm's structure changes, friction with the land alters the lower winds, and certain sectors become favorable for small-scale rotation. That means a cyclone can bring coastal flooding, inland rain, and isolated tornado damage, all within the same broader event. It is part of what makes these storms so captivating to study. They are not single hazards. They are weather systems with layers, capable of generating other violent phenomena inside themselves as they move across the landscape. The right side of a moving cyclone is often the most dangerous. In the northern hemisphere, the storm's own forward motion adds to the rotational wind on its right-hand side, which can make that sector especially destructive. It is a strange and important asymmetry. A cyclone may look like a balanced spiral on a map, yet the experience on the ground can be very uneven depending on which side you are on. Stronger winds can drive rougher seas, produce more severe structural damage, and push water inland with greater force, where the motion and rotation work together. This also affects the storm's rain bands and embedded severe weather, which can become more intense in favored sectors. That means a slight shift in track can drastically change the outcome for towns only a short distance apart. One side gets the storm at its most forceful. The other receives something less extreme. A cyclone is never just about where the center goes. It is also about which side of the center you end up facing. Forward motion can pile extra wind and surge onto one side. A moving cyclone is not simply spinning in place. It is also traveling, and that travel changes how its hazards are distributed. Where the storm's rotation and its forward speed align, winds can become stronger than they would be from rotation alone. Over the ocean, that stronger push can drive even more water toward the coast, which helps explain why one flank may face a worse storm surge than another. This added force is not dramatic in the way lightning is dramatic. It is subtle, mathematical, and relentless. Yet it can decide which shoreline floods deepest and which neighborhoods face the worst wave attack. That is why forecast cones never tell the whole story. Two places equally close to the center may not share the same fate. A moving cyclone carries its own momentum into the damage pattern, and that motion can make one side of the storm behave like a stronger version of the storm itself. Slow cyclones can be worse because they unload rain for longer. There is something especially unnerving about a storm that refuses to leave. A fast-moving cyclone may strike hard and keep going, but a slow one can sit over the same region and pour out rain hour after hour, sometimes day after day. Rivers rise. Soil becomes saturated. Drainage systems fail. Small streams turn into violent brown channels that cut across roads and fields. The danger grows not from one dramatic burst, but from relentless accumulation. Wind damage may matter most at first, yet the longer disaster is often written in water. A stalled or crawling storm can turn an already serious event into a prolonged flood emergency that spreads far beyond the coast. This is why a weaker cyclone is not always a lesser threat. When motion slows, time becomes part of the hazard. The atmosphere keeps feeding rain into the same landscape, until the land can no longer absorb or redirect what is falling from above. Fast cyclones can spread damaging winds across enormous regions in very little time. Speed creates a different kind of danger. When a cyclone moves quickly, communities have less time to react to changing conditions, and damaging weather can be delivered across a huge swath of land before recovery even begins in the places first hit. The storm's wind field sweeps onward, carrying squalls, power outages, and structural damage from one region into the next with startling efficiency. For forecasters and emergency planners, this means the hazard is not only about intensity. It is also about how fast the impact zone is expanding. A rapidly moving storm can feel like a traveling front of trouble, knocking down trees in one area while flooding roads and tearing roofs in another only hours later. That pace can overwhelm response systems because the crisis shifts location so quickly. A cyclone in a hurry becomes a messenger of disruption across distance, proving that speed alone can turn a broad landscape into a connected chain of storm effects. Some storms loop, stall, or drift unpredictably when steering winds collapse. Most people imagine storms following smooth, curved paths across weather maps, but sometimes the larger atmospheric currents that normally guide them weaken or break apart. When that happens, a cyclone can slow to a crawl, wobble in place, or even trace a loop that looks almost impossible. These strange motions can be some of the hardest to forecast because the storm is no longer being carried confidently by the broader flow. Instead, it lingers in a kind of steering vacuum, vulnerable to small influences that might barely matter in a stronger pattern. For people on the ground, that uncertainty is deeply unsettling. A storm that was supposed to leave may turn back. A coastline that expected a glancing blow may face repeated battering. These wandering tracks reveal that cyclones are not only engines of wind and rain. They are also travelers in a larger atmosphere, and when the roads of the sky fade, their paths can become surprisingly erratic. Cyclones weaken over land because they lose their warm, wet fuel source. The moment a tropical cyclone moves inland, it begins leaving behind the environment that made it possible. The ocean had been supplying heat and moisture continuously, feeding the thunderstorms around the core and helping the circulation stay organized. Over land, that supply is cut off. Friction also increases as the storm passes over forests, cities, hills, and uneven terrain, which disrupts the smooth flow that existed over open water. The circulation becomes less efficient. Thunderstorms may lose symmetry. Winds begin to drop. This is why landfall is often described as the start of weakening, even when the storm still looks formidable. Yet the process is fascinating because it shows how dependent these systems are on their birthplace. A cyclone is not a self-powered object that can roam indefinitely. It is a partnership with the sea. Once that partnership ends, the storm starts to decay, and the great ocean engine begins to come apart over the land. Yet some keep their identity for days after leaving the ocean. Even while weakening, a tropical cyclone does not always unravel at once. Some retain a recognizable center, organized rain bands, and a distinct circulation far inland, traveling for days after their connection to the sea has been broken. This lingering identity can make them feel almost ghostly, as though the ocean-borne storm is haunting the continent long after it should have faded. Moisture stored within the system helps sustain its cloud shield and rainfall, while a strong existing circulation can survive the transition better than a weaker one. In flatter terrain, the structure may remain coherent for surprisingly long distances. This matters because people inland may assume the system arriving is only a leftover low-pressure area, when in fact it still behaves like the decaying remains of a tropical storm. The name may be dropped and the peak winds may be gone, yet the storm can still carry recognizable character. Some cyclones do not vanish at landfall. They linger, diminish, and travel onward. Remnant cyclone moisture can revive floods 1,000 miles from the coast. A storm does not need hurricane-force winds to remain dangerous. Even after the organized core weakens, the surviving plume of tropical moisture can be carried deep inland and then drawn into other weather systems, mountains, or frontal boundaries. When that happens, regions far from any shoreline can suddenly receive extraordinary rainfall from what is essentially the storm's atmospheric legacy. Floods may strike places that never felt coastal wind, never saw a storm surge, and never expected a cyclone to matter to them at all. This is one of the most astonishing things about tropical systems. They can begin over warm ocean water and still end up shaping river levels far across a continent. The moisture travels, interacts, and waits for the right trigger to fall out in torrents. A cyclone's influence is not limited to its neat spiral on the satellite screen. Long after the structure decays, the water it gathered can keep writing consequences, far from where the storm was born. The strongest cyclones have central pressures lower than many airplane cabins. That comparison helps make an abstract measurement feel startlingly real. In the center of an intense cyclone, surface pressure can fall to remarkably low values, far below what people experience in everyday life, and even below the pressurized environment inside many commercial aircraft. This is not merely a technical detail for meteorologists. It is a clue to how deeply the atmosphere has been hollowed out at the storm's core. The lower the pressure falls, the steeper the contrast with the surrounding air, and that contrast helps drive the powerful winds circulating around the center. It is astonishing to think that a storm at sea can create a pocket of air pressure so unusual that it rivals conditions people associate with flight at altitude. Pressure is invisible, yet it shapes everything about the storm's behavior. The cyclone's most extreme state can be measured not only in wind and rain, but in how profoundly it reshapes the weight of the atmosphere itself. Pressure falls because rising air removes weight from the column below. This is one of the most elegant ideas in meteorology. Air has weight, and surface pressure is the result of the entire column of air above pressing downward. When air rises strongly through deep convection, some of that mass is lifted and redistributed higher up and outward from the center. With less weight pressing down at the surface, the pressure there drops. That falling pressure is not magic. It is the atmosphere physically rearranging itself. Once the drop begins, surrounding air is drawn inward toward the lower pressure, feeding the circulation and supporting more upward motion. In a cyclone, this becomes part of the engine that allows the storm to organize and strengthen. What makes it so fascinating is that something as dramatic as a tropical cyclone begins with a simple shift in balance. The sky above becomes lighter in one place than in another, and from that imbalance comes motion, convergence, and eventually one of the most formidable storms on Earth. Buoys, aircraft, ships, and satellites all help reveal a cyclone structure. No single instrument can tell the whole story of a tropical cyclone because the storm exists across a huge volume of ocean and sky. Buoys measure conditions at the sea surface where waves, pressure, and wind are directly interacting. Ships sometimes report what they encounter at the edges, adding human observations from places few people would willingly choose to be. Aircraft can cut through the storm and sample the core where the most important changes are happening. Satellites watch from above, tracing the cloud shield, the shape of the center, and the storm's movement over time. Each tool sees a different face of the same system. Together they turn a distant spiral into something scientists can diagnose almost like a living patient. That is part of the wonder of modern meteorology. A storm the size of a sea can be examined from the ocean surface, from inside the clouds, and from orbit, all at once. Hurricane hunters fly into cyclones, because satellites cannot measure everything. From space, a storm can look beautifully complete, with curved cloud bands and a neat central high. Yet some of the most important details remain hidden unless an aircraft goes in and samples them directly. Satellites can estimate intensity, but they cannot always tell with certainty what the winds are doing near the surface or exactly how low the pressure has fallen in the center. That is why specially equipped crews fly into these storms on purpose, sometimes through violent turbulence and sheets of rain, to gather the missing truth. It is one of the most remarkable jobs in science. The aircraft crosses the eye wall, enters the calmer center, then exits and repeats the process to build a clearer picture of the cyclone's condition. These flights are not acts of spectacle. They are acts of measurement. The goal is to replace educated guesses with real observations from the heart of the storm itself. Dropsondes fall through storms, reporting winds, pressure, temperature, and humidity as they descend. These small instruments are released from aircraft into the cyclone and then begin a quiet fall through one of the most violent environments on Earth. As they descend, they send back a stream of information that reveals how the atmosphere changes from high altitude down toward the sea. That vertical profile is precious because a cyclone is not a flat pattern on a weather map. It is a deep, layered structure, and conditions can be very different at one height than at another. A dropsonde lets meteorologists see those layers in motion. They can detect where the strongest winds sit, how moisture is distributed, and how pressure changes as the instrument falls through the eye wall or into the center. It is almost like lowering a tiny scientific lantern through the storm's hidden interior. For a few minutes, the atmosphere stops being guesswork and becomes a measured column from cloud top toward ocean surface. Radar can reveal hidden eye walls, rain bands, and sudden structural changes. When a cyclone approaches land, radar becomes one of the most revealing tools forecasters have. Instead of seeing only the cloud shield from above, they can watch the storm's internal arrangement in remarkable detail, sweep by sweep, as bands curve inward and new features emerge. A radar display can show an eye tightening, a ring breaking apart, or a second ring beginning to form around the first. It can also reveal where the heaviest rain is wrapping in, and where the storm's most organized inner structure is shifting. This matters because a cyclone is constantly changing, sometimes in ways that dramatically alter local impacts. Radar catches those changes close to real time. It gives the storm a skeletal look, exposing hidden architecture inside what might otherwise seem like one large mass of rain. For people near the coast, that knowledge can be crucial because a subtle structural change can mean a very different experience on the ground. Infrared satellites estimate storm strength by reading cloud-top temperatures from space. This works because the tops of the tallest thunderclouds are usually very cold, and in tropical cyclones, those cold tops often signal powerful convection surrounding the core. Infrared sensors detect that temperature pattern even at night, which makes them invaluable for constant monitoring over remote oceans. Meteorologists study the shape and intensity of those cold cloud tops, especially how they wrap around the center, to estimate how organized and potentially strong the storm has become. It is an elegant method because the storm is being judged not by what the eye can see in visible light, but by how cold its highest clouds have grown. The colder the tops, the higher and more vigorous the convection is likely to be. From thousands of miles above Earth, satellites are reading the thermal signature of a living storm. It is a striking example of how invisible properties, not just dramatic pictures, help reveal the cyclone's hidden intensity. Microwave sensors can peer through clouds and expose the storm's hidden core. Ordinary satellite pictures mostly show the outer skin of a cyclone, which can be deceptive. Thick cloud cover may hide whether the storm is truly organizing or simply looking impressive from above. Microwave instruments are different. They can sense radiation patterns that allow scientists to infer what is happening deeper inside the cloud mass, including the arrangement of rain, ice, and the storm's inner bands. That means they can sometimes reveal a forming eye, a broken eye wall, or a lopsided core long before those details become obvious in standard imagery. This is one of the great marvels of modern observing. The storm seems sealed behind dense cloud, yet remote sensing can still uncover its internal layout. For forecasters, that deeper view can completely change the interpretation of a system. A cyclone that appears healthy on the outside may be disorganized within, while another that looks messy may secretly be building the structure needed for rapid strengthening. Cyclone forecasts improved dramatically once meteorologists began assimilating satellite data. Before the satellite era, vast stretches of ocean were observational blind spots, and storms could develop, intensify, or curve without being fully understood. Once satellite information began feeding directly into forecasting systems, that changed the science of tropical cyclones in a profound way. Assimilation means the data are not simply viewed by humans. They are incorporated into weather models, so the atmosphere those models start with is much closer to reality. Cloud patterns, wind estimates, moisture fields, and temperature structure all help create a better opening portrait of the storm and its environment. Better beginnings usually lead to better forecasts. That improvement has saved lives because it allows earlier warnings, sharper track guidance, and a more complete understanding of what the storm is doing over open water. It is astonishing to think how much changed when humanity began watching the oceans continuously from space and then teaching machines to use that view intelligently. Even now, track forecasts are usually better than intensity forecasts. That may seem backward at first. Surely it should be easier to predict how strong a storm becomes than where it will travel. In practice, the opposite is often true. A cyclone's path is strongly influenced by large-scale atmospheric patterns, and those broader steering currents are often easier for models to represent well. Intensity depends on much smaller and more delicate processes inside the storm and just around it. Tiny differences in core structure, ocean conditions, moisture, or upper winds can lead to very different outcomes. A storm might follow the expected route almost perfectly, while still becoming much stronger or weaker than predicted. This is one reason cyclone forecasting remains such a humbling science. We can often tell communities where the danger is heading with impressive skill, yet still struggle to say exactly what form that danger will take when it arrives. The storm's road is clearer than its mood. Predicting where a cyclone goes is easier than predicting how strong. A storm's movement is shaped by the larger weather patterns surrounding it, almost like a boat being carried by broad currents in the sky. Those currents can usually be mapped and modeled with reasonable success, especially a few days ahead. Strength, by contrast, depends on what is happening in the cyclone's compact inner engine, where small shifts can have dramatic effects. A tiny change in the eye wall, a brief intrusion of dry air, or a subtle improvement in upper-level ventilation can alter the storm's future quickly. That makes intensity feel more personal to the cyclone itself, tied to its internal health, rather than simply its surroundings. It is a bit like knowing where a traveler is going, but not knowing whether they will arrive exhausted or energized. The destination can be easier than the condition. That contrast helps explain why forecast cones have become familiar, while sudden surprises in storm strength still capture public attention and scientific concern. Tiny changes in ocean heat can produce big changes in storm strength. A difference that seems minor on a map can matter enormously to a cyclone. Slightly warmer water can increase evaporation, support stronger convection, and help the storm maintain a more efficient inner core. Slightly cooler water can do the opposite, nudging the system toward weakening or at least slowing its growth. What makes this fascinating is that the atmosphere is responding to subtle changes in the sea, with consequences large enough to alter evacuation plans and impact forecasts. A storm does not experience the ocean as a flat blue surface. It experiences it as a shifting field of energy availability. Crossing a small boundary between one water mass and another can change what the cyclone is capable of doing next. That sensitivity is one reason intensity forecasting remains so challenging. Enormous storms can hinge on details that look almost trivial at first glance, proving that in tropical meteorology, small thermal differences can have very large human consequences. Warm water depth matters because shallow warmth can be mixed away quickly. A cyclone does not feed on a thin skin of warmth alone. If only the uppermost layer of the sea is warm, the storm's own winds can churn that surface water and pull cooler water up from below. Once that happens, the energy supply can fade surprisingly fast. The cyclone has, in a sense, stirred away its own fuel. But when the warmth extends deeper, mixing does less immediate damage, and the storm can keep drawing energy from below the surface. That hidden depth is why two equally warm-looking patches of ocean can produce very different outcomes. From above, they may seem identical. To a cyclone, they are not. One is a shallow promise that vanishes when disturbed. The other is a deep reservoir that keeps giving. It is one of the most fascinating secrets of tropical weather, because the future of a storm can depend not just on surface temperature, but on how far that warmth reaches into the sea. Some cyclones churn colder water upward and weaken themselves in the process. There is something almost poetic about a storm helping to undo its own strength. As intense winds rake across the ocean, they stir the upper layers and can draw cooler water up from below. That cooler water reduces evaporation and weakens the heat exchange that had been powering the storm. In effect, the cyclone can begin exhausting the conditions that made it possible. This self-limiting process is especially important for slower-moving storms because they remain over the same patch of ocean long enough to disturb it more thoroughly. The sea beneath them changes from energy source to partial break. Scientists sometimes see a clear, cool wake left behind a passing cyclone, a ribbon of altered ocean that marks where the storm has spent part of the surface heat. It is a powerful reminder that these systems do not simply act upon the ocean. They also transform it, and sometimes that transformation becomes the very reason the storm starts to fade. Others cross deep, warm pools and suddenly explode in strength. In some parts of the ocean, the heat extends downward in thick layers, creating a kind of hidden reserve beneath the surface. When a cyclone passes over one of these deep, warm pools, its winds may churn the sea, yet still fail to bring enough cool water up to starve the storm. Instead, the heat remains available, and the cyclone can intensify with astonishing speed. This is one of the most dramatic interactions between ocean and atmosphere. To an observer, the storm may seem merely to be continuing its track. Underneath, it has reached a richer energy source, and the response can be immediate. The central structure tightens. Convection strengthens. The storm begins to look more powerful almost by the hour. Forecast centers watch these regions closely because they know the sea itself may be preparing a sudden change. A deep, warm pool is like a hidden staircase, and the cyclone can race upward before people on land fully grasp what is happening. El Niño and La Niña can reshape cyclone seasons across whole oceans. These climate patterns are not storms themselves, yet they alter the background state of the tropical atmosphere in ways that matter enormously for cyclones. During El Niño and La Niña, large regions of the Pacific warm or cool in unusual ways, and that shifts winds, rainfall patterns, and the placement of rising and sinking air across the globe. Those changes can make one ocean basin more favorable for cyclone formation, while making another less inviting. In some regions, seasons become busier. In others, storms become fewer, or their preferred tracks shift. What makes this so fascinating is the scale. A change spread across an ocean can quietly influence where spinning storms are likely to emerge months later. It is weather linked to climate, and climate linked to remote patches of sea surface temperature. A cyclone season does not arise from local conditions alone. It is also shaped by planetary patterns that stretch across the tropics, like slow, powerful adjustments in the atmosphere's great machinery. The Atlantic, Pacific, and Indian Oceans each produce cyclones in distinct ways. The same kind of storm can feel different depending on the basin where it forms. The Atlantic is strongly shaped by tropical waves rolling west from Africa, by changing wind shear, and by the peculiar geography of warm currents, islands, and continental coastlines. The Pacific contains enormous stretches of warm water and multiple active regions, from the eastern basin to the especially prolific western side. The Indian Ocean has its own seasonal rhythms, including influences from monsoon winds, and a different arrangement of land and sea that affects where storms form and where they strike. These basins are all parts of one planet, yet each teaches cyclones a slightly different style. The atmosphere speaks the same language, but with regional accents. That is one reason tropical meteorology is so rich. You are not studying one uniform system repeated endlessly. You are studying a global family of storms, each basin offering its own version of how heat, spin, moisture, and geography come together. The North Indian Ocean has fewer storms, but often deadlier coastal exposure. This basin does not usually produce as many tropical cyclones as the Western Pacific, yet the human stakes can be immense. Around the Bay of Bengal in particular, low-lying coasts, large populations, river deltas, and intense storm surge vulnerability can combine to make landfall especially catastrophic. A single event can affect millions of people across densely settled areas where water has little difficulty spreading inland. The shape of the coastline and the shallow waters nearby can worsen the flood threat, while the timing of storms around the monsoon seasons adds further complexity. Historically, some of the deadliest cyclone disasters on Earth have unfolded here. Not because the storms are always the strongest in absolute terms, but because the exposure is so severe. This makes the basin unforgettable to study. It shows that cyclone danger is never only about meteorology. The same spinning system becomes more lethal when it meets a coastline where geography and human settlement leave little room for error. The Western Pacific produces more tropical cyclones than any other basin. This vast stretch of ocean is the world's great workshop for tropical cyclones. Warm waters, broad open fetch, and a favorable tropical environment often combine to produce more storms here than anywhere else on Earth. The basin is so large that systems can form, strengthen, curve, and travel across enormous distances, sometimes threatening multiple countries during a single life cycle. This abundance has shaped the meteorological culture of the region, where storm tracking is a central part of life in many coastal nations and islands. It also means the Western Pacific offers scientists an extraordinary natural laboratory. Here they can observe nearly every variation of tropical cyclone behavior, from compact violent storms to sprawling long-lived giants. The sheer number of systems makes the basin feel relentless in active years, as though the atmosphere has found one of its favorite stages. For anyone trying to understand cyclones on a global scale, the Western Pacific is impossible to ignore. The South Atlantic almost never grows tropical cyclones, but rare exceptions happen. That rarity makes every exception feel startling. The South Atlantic is usually hostile to tropical cyclone development because the water is often not warm enough over a broad area, Wind shear tends to be unfavorable, and the larger atmospheric setup does not often support the organized tropical structure these storms require. For that reason, many people long assumed the basin was essentially off-limits. Yet nature occasionally refuses tidy rules. Under unusual circumstances, a storm can still acquire tropical characteristics there, reminding meteorologists that low probability is not the same thing as impossibility. These rare events are scientifically thrilling because they force researchers to ask exactly which barriers were briefly lowered and why. When a South Atlantic tropical cyclone does appear, it feels like the atmosphere has produced a rare note outside the expected score. The basin remains one of the least likely places for such storms, which is precisely why the exceptions are remembered so vividly. Medicanes are small, cyclone-like storms that sometimes form over the Mediterranean. The name combines Mediterranean and hurricane, and it points to something genuinely unusual. These storms are typically much smaller than true tropical cyclones, yet they can develop a compact eye-like feature, organized bands, and a warm core structure that gives them a tropical flavor. They form in a sea not usually associated with classic hurricanes, which is part of what makes them so captivating. The Mediterranean is semi-enclosed, surrounded by land, and far smaller than the great tropical basins, so when a storm begins to resemble a miniature cyclone there, it feels almost improbable. Medicanes are not simply ordinary low-pressure systems with dramatic branding. Some genuinely share structural traits with tropical storms, though they often arise through a more mixed set of ingredients. They are a reminder that cyclone-like behavior can emerge in unexpected corners of the planet. Even an inland sea with ancient coastlines can, on rare occasions, produce a spinning storm of surprising character. Subtropical cyclones blur the line between tropical and mid-latitude weather systems. These storms occupy a fascinating middle ground. They are not fully tropical in the classic sense, yet they are not ordinary cold core systems of the temperate zones either. A subtropical cyclone often has a broader wind field, with the strongest wind set farther from the center, and it may draw energy from both warm ocean waters and temperature contrasts in the surrounding atmosphere. That mixed heritage makes it feel like a hybrid, part tropical engine and part mid-latitude disturbance. For forecasters, these storms can be tricky because their structure may evolve. Some gradually become more tropical over time, tightening their core and reorganizing their convection. Others remain stubbornly in between. For the public, the label may sound technical, but the concept is wonderfully revealing. The atmosphere does not always obey neat categories. Sometimes it creates transitional forms, storms that sit between familiar boxes and show that weather is a spectrum, not a set of perfectly separate compartments. Extratropical cyclones are different beasts, powered mainly by temperature contrasts, not warm seas. These storms belong to a different branch of the cyclone family. Instead of drawing most of their power from warm ocean water and deep tropical moisture, they thrive on clashes between air masses of different temperatures. Cold air pushes against warm air. Boundaries sharpen. The atmosphere begins converting those horizontal contrasts into motion, cloud, wind, and sweeping weather fronts. That is why extratropical cyclones often come with long arcs of rain, snow, or shifting wind, rather than the tight, symmetric core of a tropical system. They can grow huge, sometimes spanning vast regions and affecting many countries at once. In the middle latitudes, they are among the most important engines of everyday weather. What makes them so fascinating is that they reveal another way the atmosphere can build a giant spinning system. The planet does not need tropical heat alone. It can also generate cyclones from imbalance itself, from warm and cold air trying to sort themselves out across the sky. Some tropical cyclones transform into powerful extratropical storms instead of simply dying. A cyclone leaving the tropics does not always fade into a shapeless remnant. Sometimes it begins a remarkable metamorphosis. As it moves into cooler waters and stronger upper winds, the storm can lose its tropical symmetry and start interacting with temperature boundaries in the surrounding atmosphere. Its warm core weakens, fronts begin to form, and the system changes from a compact tropical engine into a broader, extratropical one. Yet that change does not necessarily mean harmless. In some cases, the storm grows larger, its wind field expands, and it becomes a formidable system in a new way. The identity changes, but the power can remain. This is one of the most dramatic afterlives in meteorology. A storm born over warm tropical seas can travel poleward and reinvent itself as a different kind of cyclone altogether. It does not merely vanish. It changes energy source, changes structure, and continues the journey under a new atmospheric logic. Polar lows are tiny, fierce cyclones that whirl over cold, high-latitude seas. These storms are small compared with tropical cyclones, but they can be startlingly intense for their size. They form over cold oceans in high latitudes when frigid air pours across relatively warmer water, creating a burst of instability that can build tight spirals of cloud, snow, and violent wind. Seen from satellites, some look like miniature hurricanes dropped into the Arctic or subarctic, compact and sharply defined against a grey world of sea and ice. Their small scale makes them especially dangerous to ships and coastal operations because they can intensify quickly and remain hard to predict in detail. What makes them so captivating is the contrast. Tropical cyclones belong to warm seas and humid air. Polar lows are creatures of cold, thriving in a harsher atmospheric setting, yet still forming recognizable spinning structures. They show that cyclone-like weather is not reserved for the tropics. Even near the frozen edges of the world, the atmosphere can still whirl itself into a storm. Cyclones also rage on other worlds, where they become even stranger. Once you lift your eyes beyond Earth, the idea of a cyclone becomes far more wondrous. Other planets and moons have atmospheres too, and where there is atmosphere, rotation, temperature contrast, and fluid motion, there can be spinning storms. But away from Earth, the ingredients change. The gases are different. The scales are different. The lifetimes can be extraordinary. A cyclone on another world may not involve rain in the earthly sense at all. It may spin through hydrogen, methane, or dust under skies unlike anything humans have ever stood beneath. Some last far longer than storms here. Some form shapes that seem almost geometric. Studying them reminds us that cyclones are not merely weather events on one planet. They are expressions of a deeper rule about moving fluids on rotating worlds. Earth storms are part of a much larger cosmic story, where atmospheres everywhere find ways to turn imbalance into spirals, vortices, and enduring motion. Jupiter's Great Red Spot is a colossal cyclone older than some nations. This storm is so vast that Earth itself could fit inside it, and it has been observed for centuries. That alone makes it one of the most astonishing atmospheric features known to science. It churns in Jupiter's thick atmosphere as an immense anticyclonic vortex, fed not by oceans, but by the fluid dynamics of a giant gas planet with no solid surface in the familiar sense. Its reddish color, shifting size, and persistent motion have fascinated astronomers since telescopes first revealed it as more than a mere blemish. What feels most uncanny is its age. On Earth, storms come and go in days or weeks. Jupiter's great vortex has endured through generations, wars, inventions, and whole chapters of human history. It turns the idea of weather into something almost geological in timescale. A storm that outlives empires changes how you think about atmospheres. It suggests that on some worlds, the sky can remember. Saturn has a bizarre hexagon near its pole with a cyclone at center. Few sights in planetary science are stranger than a six-sided jet stream wrapped around a polar cyclone. At Saturn's North Pole, winds organize into a huge hexagonal pattern that has persisted for decades of observation. And at the middle of that geometric frame sits a spinning storm. The combination feels almost unreal, as though mathematics itself has been etched into the atmosphere. Scientists think the hexagon is a standing wave in Saturn's winds rather than a solid structure, yet its sharp shape remains one of the great visual wonders of the solar system. At the center, the polar cyclone adds another layer of mystery, a deep vortex embedded inside this giant atmospheric pattern. Together, they show that cyclones on other worlds can be shaped by dynamics unlike anything common on Earth. A terrestrial storm already seems extraordinary. Saturn reminds us that elsewhere, the sky can go beyond spirals and produce forms that look almost impossibly deliberate. Mars can produce spinning dust storms, though they are not tropical cyclones. Mars lacks warm tropical oceans, dense humid air, and the deep convection that power Earth's tropical cyclones, so its spinning storms belong to a different category. Yet the red planet is far from calm. Dust devils wander across its surface, and larger dust storms can grow so immense that they spread across huge regions or even engulf much of the planet. In those storms, fine particles are lifted and carried through a thin atmosphere, turning the sky hazy and dim. The result is weather that feels both familiar and alien. There is rotation, turbulence, and large-scale atmospheric drama, but without rain bands, eye walls, or wall motion heat. For planetary scientists, Mars is a reminder that a storm need not resemble an earthly cyclone to be mesmerizing. A world of dust can still whirl. The comparison also sharpens our appreciation of Earth, where the presence of oceans and abundant water vapor allows spinning systems to become lush, wet, towering structures instead of dry airborne veils. On Earth, cyclone seasons peak when oceans are warmest and winds are favorable. There is a rhythm to the year in every cyclone basin, and that rhythm follows the slow preparation of the ocean and atmosphere. As sunlight warms the sea over months, surface waters become more capable of feeding deep convection. At the same time, larger wind patterns shift, and in certain seasons, they become more supportive of storm organization rather than hostile to it. The result is a window when the ingredients are most likely to align. That is why cyclone activity does not occur randomly across the calendar. It pulses with seasons, reaching a peak when stored ocean heat and atmospheric conditions meet in the right balance. Yet each basin has its own timing, shaped by geography, monsoon cycles, and hemispheric differences. This makes cyclone season feel less like a date range on paper and more like a recurring planetary mood. The world turns, the seas warm, the winds adjust, and the atmosphere becomes more willing to spin. The official season matters, but nature does not always respect calendars. Season dates are useful because they mark the period when cyclones are most likely, helping governments, forecasters, and communities prepare. But the atmosphere does not consult a printed schedule. If ocean warmth, moisture, and wind conditions come together earlier or later than expected, a storm can still form outside the official bounds. That is why pre-season and post-season cyclones sometimes surprise people who assumed the danger window had not yet opened or had already closed. The official season is a statistical guide, not a physical barrier. Nature works through conditions, not ceremony. This is one of the more humbling truths about weather. Humans create neat categories because they help organize action and memory. the atmosphere remains gloriously indifferent to them. A basin may usually behave one way, then offer a reminder that averages do not rule individual events. A cyclone outside the season feels startling precisely because it exposes the difference between our calendar and the planet's actual timing. Some cyclone names are retired forever after especially deadly or costly storms. When a storm's name becomes inseparable from extraordinary loss, that name is often removed from future lists. It is a small but powerful act of memory. Names are meant to help communication, yet after a truly devastating cyclone, repeating the same name years later would feel jarring, almost disrespectful to those who lived through the original disaster. Retirement acknowledges that some storms leave a mark too deep for routine reuse. The name becomes historical rather than operational. For viewers and listeners, this can be one of the most human details in all of meteorology. Beneath the science of pressure, wind, and rainfall lies a record of grief, survival, and collective remembrance. A retired name is evidence that the storm crossed into culture and history. It stopped being just one event among many. It became a reference point, a word that now carries ruined coastlines, emergency broadcasts, family stories, and the knowledge that one storm can change how a generation hears a name. Naming storms helps the public remember warnings and track separate threats clearly. Before storms were consistently named, it was much easier for confusion to creep into forecasts, reports, and public conversation. A name gives a cyclone a clear identity, which matters enormously when more than one system exists at the same time or when a storm lasts long enough to dominate headlines for days. People remember names better than technical coordinates or vague descriptions of a low-pressure area over the sea. That memory helps warnings stick. It also helps families, officials, and newsrooms keep one threat separate from another, without mixing details or locations. In a busy season, that clarity can be life-saving. A name turns a moving weather system into something the public can follow from update to update with less uncertainty. It is one of those simple inventions that seems obvious only after it works. The science of forecasting may be complex, yet public safety often improves through something as human and memorable as giving the storm a proper name. Human names replaced older latitude-longitude labels because people remembered them more easily. Imagine trying to follow a dangerous storm called by nothing more than its position on a map, a string of numbers that shifts with every update and means little to anyone not trained to pass coordinates quickly. That older style was precise in one sense, yet awkward for public communication. Human names changed that. They made storms easier to remember, easier to discuss, and much easier to distinguish in broadcasts, newspapers, and emergency planning. Once a name enters public conversation, it travels naturally from forecasters to families, from radio bulletins to kitchen tables. That matters because warnings only help when people can hold on to them. A memorable name gives the storm a stable verbal identity, while its location keeps changing. There is something revealing in that choice. Meteorology advanced not only by building better instruments and models, but also by learning how people actually listen, remember, and respond when weather becomes dangerous and time is short. Cyclone categories describe wind, but they do not capture every deadly hazard. A category can be useful because it gives a quick sense of how strong a storm's winds have become. But that number does not summarize the whole danger. It says little about rainfall totals, about storm surge shaped by coastline and tide, or about how long the system may linger over one place. A lower category can still drown communities underwater, while a higher category in a different setting may produce a very different outcome. This is one reason tropical cyclones can be so misunderstood. People often want a single number that tells the whole story, yet the atmosphere rarely offers such simplicity. A category measures one important feature, not the complete experience of landfall. The real threat lives in the combination of hazards and in where the storm strikes. That makes cyclone warning more like interpretation than scorekeeping. Wind matters deeply, but the storm is always more than its label on the scale. A lower category storm can still cause historic flooding and devastating loss. This fact unsettles people because it breaks the instinct to rank danger by wind alone. A storm that is not at the top of the category scale can still move slowly, carry vast moisture, strike vulnerable terrain, or arrive where rivers, streets, and floodplains are poorly prepared to handle extraordinary double E. Rain. In those cases, water becomes the author of the disaster rather than wind. Homes may remain standing while neighborhoods are submerged. Trees may survive while roads vanish and bridges fail. The damage can be immense, and the human toll can be heartbreaking, even though the storm never wore the most extreme wind label. That is why experienced forecasters often stress impacts over category. The atmosphere does not care whether a system sounds modest on paper. If the setup favors flooding, the consequences can become historic. A cyclone's danger lies in what it does to a place, not simply in how fast its peak winds were measured. Stronger categories often mean worse wind damage, but local impacts vary wildly. Two towns can face the same cyclone and come away with entirely different stories. One may lose roofs, windows, and power for weeks, while another, only a short distance away, escapes with fallen branches and scattered debris. Part of that difference comes from which side of the storm passes closest. Part comes from terrain, building quality, elevation, vegetation, and even the angle of nearby coastlines. Wind categories do reflect real increases in destructive potential, yet they cannot describe every local outcome because no storm strikes a blank canvas. It hits a particular place with its own vulnerabilities and strengths. That is what makes cyclone damage so uneven and so fascinating to study. A category tells you something important about the storm. It does not tell you everything about the meeting between that storm and a specific community. Local impact is where meteorology meets geography, engineering, chance, and the stubborn details of real life. Building design can decide whether the same cyclone becomes a crisis or a scare. The storm may be identical in wind and rain, yet the outcome can differ dramatically depending on what it meets on land. A well-built home with strong roof connections, protected openings, and careful construction details may endure conditions that would tear apart a weaker structure nearby. The difference can come down to choices that seem mundane before the storm arrives: how the roof is fastened, how the walls are tied together, whether doors and windows resist flying debris. Once the outer shell is breached, pressure and rain can do far more harm inside. That is why engineering matters so much in cyclone country. It changes the story from inevitable destruction to survivable impact. This does not remove danger, of course, and no building is invincible. But design can shift the odds in powerful ways. A cyclone tests more than weather forecasting. It tests the built world, and sometimes the answer depends on bolts, brackets, and planning. Mangroves and reefs can reduce surge and waves before they reach shore. These natural systems do not stop a cyclone, and they are not magical shields, but they can take some of the force out of the water before it reaches homes and roads. Coral reefs help break incoming waves offshore, reducing some of the energy that would otherwise slam directly into the coast. Mangrove forests slow moving water with dense roots and trunks, trapping sediment and disrupting the inland push. Together, they create a rougher, more resistant path between open sea and vulnerable land. That matters because storm damage is often a story of momentum. The more energy the coast can absorb or scatter before the surge arrives, the better the chances for what lies behind it. There is something beautiful in that. A living shoreline can serve as part of a community's protection. Ecology becomes defense. Reefs and mangroves are not only habitats full of marine life. In cyclone country, they can also be quiet partners in survival. Wetlands act like natural shock absorbers when cyclones push the sea inland. When surge moves across a coast lined with marshes, swamps, and tidal flats, that water meets a landscape that can spread, slow and partly absorb its force. Vegetation creates friction. Broad, wet areas give the water space to disperse instead of rushing unbroken towards streets and houses. In that sense, wetlands behave a little like a buffer zone built by nature over centuries. The effect is not absolute, and a major storm can still overwhelm them, yet their presence can reduce the speed and intensity of what reaches inland communities. Lose those wetlands, and the coast often becomes more exposed. The sea has a clearer run at the land. This gives wetlands a quiet grandeur that is easy to overlook in calm weather. They may seem muddy, flat, and ordinary. During a cyclone, they reveal another identity. They become part of the coastline's resilience, soft ground standing between rising water and the places people call home. Warmer oceans can increase the odds of extreme rainfall in tropical cyclones. A warmer sea surface can feed more evaporation into the lower atmosphere, and a moister atmosphere has more water available to fall as rain when a cyclone organizes that moisture into deep convection. The result is not that every storm automatically becomes a rainfall record, but that the ceiling for extreme downpours can rise. In the right conditions, tropical cyclones may be able to wring more water out of the air than they once did. This is one reason rainfall has become such an important part of the climate conversation around cyclones. The drama is not only in the wind or the surge at the coast. It is also in how much water the storm can carry and release over land. A warmer ocean does not simply sit there passively. It helps load the atmosphere. Then the cyclone arrives and turns that invisible loading into torrents, swollen rivers, flooded neighborhoods, and disasters measured in depth rather than gust speed. Rising seas make storms surge right in from a higher starting line. Even if a cyclone were identical in every other respect, higher background sea levels would still matter because the ocean is beginning from an elevated baseline before the storm ever arrives. That means surge has less vertical distance to climb before it reaches thresholds that flood roads, overtop barriers, and enter buildings. In practical terms, water that once stayed just below danger levels may now cross them more easily. The storm does not need to be stronger for the impacts to worsen. The platform beneath it has already risen. This is one of the clearest ways long-term change and short-term weather interact. A cyclone is an event. Sea level rise is a shifting backdrop. Put them together, and familiar coasts may face deeper flooding from storms that would once have caused less damage. It is a sobering idea because it changes the meaning of past experience. What used to be survivable by a narrow margin may no longer be enough. Climate change does not create cyclones, but it can worsen some impacts. Tropical cyclones existed long before factories, engines, and satellites, so they are not inventions of the modern world. What changes is the background environment in which they form and make landfall. A warmer atmosphere can hold more moisture, which can raise the potential for heavier rainfall. Higher sea levels can make surge more damaging even when the storm itself is not unprecedented. In some regions, warmer ocean conditions may also increase the chance that the strongest storms reach very high intensity. None of this means every season will look the same, or that every cyclone can be blamed on one cause. Weather remains complex and variable, yet the stage on which these storms act is shifting, and that matters. The cyclone is still a natural engine of heat, water, and spin. What has changed is that some of the surrounding conditions now make its consequences harder to contain once it arrives at vulnerable coasts and river basins. Ancient sediments preserve signs of cyclones that struck long before written history. Long before humans kept storm records, the coast was keeping its own. In lagoons, marshes, blue holes, and quiet coastal basins, powerful cyclones sometimes pushed sand and marine debris far inland, laying down distinct layers that remained trapped in the mud. Over centuries, those layers stacked up like pages in a hidden archive. Scientists can extract cores from these sediments and read them from top to bottom, tracing episodes when the sea invaded unusually far and left behind a signature different from ordinary tides or seasonal rain. Flooding. Dating those layers reveals storms that struck places hundreds or even thousands of years before written observation. It is an extraordinary kind of history. No names, no warnings, no eyewitnesses, only grains of sand in the wrong place telling the story of a past landfall. Sediment records remind us that coasts have long memories, and the storms of the deep past are still faintly preserved beneath our feet. Tree rings and cave deposits can hold clues to storms from past centuries. Nature keeps records in unexpected forms. In some forests, unusually severe storm damage can alter tree growth for years, leaving patterns in the rings that hint at disturbance, salt exposure, or sudden ecological change. In caves, mineral deposits grow layer by layer as water drips from above, and the chemistry of those layers can preserve signals linked to intense rainfall or shifts in moisture brought by past cyclones. Neither archive tells a simple story on its own, yet together with other evidence they help scientists stretch the storm record backward beyond the era of modern instruments. What makes this so fascinating is the subtlety. A cyclone passes in fury and noise, but its traces can survive in wood grain and stone drip, stored quietly for generations. The storm is gone. The memory remains. To study old cyclones, researchers do not only read logs and maps. They read trees, caves, and the slow, natural records built over time. Historical ship logs helped scientists reconstruct cyclone patterns before satellites existed. Before weather satellites watched the oceans day and night, mariners were often the only witnesses to storms far from land. Captains recorded pressure, wind direction, sea state, cloud cover, and sudden changes in weather because their lives depended on it. Those entries, written in cramped handwriting across countless voyages, became an accidental scientific treasure. By gathering many logs from different ships and dates, researchers can piece together where storms likely traveled, how intense they may have been, and which ocean regions were active long before modern monitoring. It is a kind of detective work across time. A falling barometer here, a veering wind there, towering seas reported days apart by different vessels, and slowly the outline of a lost cyclone emerges. The idea is beautiful in its own way. Sailors who were simply trying to survive left behind fragments that now help science reconstruct the forgotten behavior of storms over oceans once hidden from view. Some coastlines bear visible scars from storms that struck generations ago. A major cyclone can leave marks that outlast the people who first witnessed them. New inlets may cut through barrier islands. Entire stands of trees may vanish and never fully return. Coastal lakes can become saltier after the sea is driven into them, altering the landscape for decades. Ridges of sand thrown inland by surge may remain as subtle lines across marsh or forest, and eroded bluffs may never reclaim what was lost. In some places, you can stand on a modern shore and still see the long memory of an old landfall written into the shape of the land. That endurance changes how a coastline feels. It stops seeming like a finished place and starts seeming like a place still carrying evidence of former violence. Storms do not merely pass. Sometimes they leave physical signatures that become part of local geography, quiet reminders that a single night of wind and water can alter the land for generations. Cyclones can reshape ecosystems by opening forests and flooding estuaries with salt. When a strong storm passes through a coastal landscape, it does more than damage human structures. It can rip open forest canopies, topple old trees, bury roots in sediment, and push salt water deep into wetlands and estuaries that usually balance fresh and brackish conditions more delicately. Suddenly, sunlight reaches the forest floor, where shade once ruled. Freshwater species struggle in places that have turned salty. Fish nurseries, marsh plants, microbes, and birds all face a changed environment. Some habitats recover quickly. Others shift into something new. This is why ecologists often study cyclones not just as disasters, but as agents of ecological reset. The storm redistributes water, light, nutrients, and living space in one violent episode. A landscape that seemed stable can be rearranged into a different pattern of life. In that sense, a cyclone is not only a weather event. It is also a force that edits the living map of a coast. Certain species actually depend on cyclone damage to renew habitat and nutrients. That sounds counterintuitive at first, because destruction feels like the opposite of ecological health. Yet in some environments, periodic storm damage helps keep habitats dynamic. A cyclone can knock down dense vegetation and create openings where new plants can grow. It can wash nutrients into estuaries and floodplains, feeding bursts of productivity once the waters settle. In forests, gaps created by windthrow may allow light-loving species to return. On coasts and islands, some birds, fish, and invertebrates benefit indirectly from the fresh mix of space, sediment, and organic material left behind. This does not make storms kind or harmless. It means ecosystems have evolved under their influence. Over long timescales, life has learned not only to endure disturbance, but sometimes to use it. That is one of the deepest lessons cyclones offer. A storm can be ruinous for individuals, yet still play a recurring role in the renewal and reshaping of entire living communities. Seabirds, sharks, and turtles can sense approaching storms in remarkable ways. Animals often react before humans notice much at all. Seabirds may alter their flight paths or head for shelter as pressure falls and winds begin to shift. Some sharks have been observed moving into deeper or calmer waters ahead of major storms, while sea turtles can change behavior in response to the changing sea state and pressure patterns around them. Scientists are still learning exactly which cues matter most, whether it is barometric pressure, low-frequency sound, changing wave motion, or some combination of signals that animals read more finely than we do. What makes this so captivating is that these creatures are not consulting forecasts. They are responding directly to the atmosphere and ocean in real time. Their bodies are tuned to environmental change in ways ours often are not. A cyclone may announce itself to them long before it announces itself clearly to us, which gives approaching storms an almost invisible biological ripple through the natural world. Flying insects sometimes vanish before cyclones, as pressure changes sweep through the air. Anyone who spends time outdoors before major weather shifts may notice a strange hush, not always in sound, but in movement. In some cases, flying insects seem to disappear or sharply reduce activity as pressure drops and the atmosphere grows unsettled. For small airborne creatures, this makes sense. Falling pressure, stronger gusts, and rising humidity can signal dangerous conditions ahead, and staying grounded may be safer than risking chaotic air. Scientists have found that some insects are sensitive to barometric changes and can alter behavior well before the storm arrives in full force. That sensitivity adds a subtle layer to the story of cyclones. The atmosphere begins changing long before landfall, and tiny animals respond to those early signs. A storm, then, is not only the dramatic moment of impact, it is also the quiet withdrawal before it, when the air changes character and even the smallest flyers seem to sense that the sky is becoming unfriendly. People often fear the "I is the end," then the backside strikes. The arrival of the "I can" be one of the most deceptive moments in any cyclone. After hours of roaring wind and rain, the world may suddenly ease. The sky can brighten. The air can turn oddly still. People step outside, thinking the storm has passed, when in fact, they have only reached its center. Around them, the eye wall still exists as a ring of violent weather, and the second half is approaching fast. When it arrives, the wind reverses direction and attacks everything already weakened by the first half. Loose debris becomes dangerous again. Damaged roofs fail more easily. Trees, stressed one way, are pushed back the other. That false lull has trapped countless people through history because the calm feels persuasive. It feels final. But the eye is not an ending. It is an interval inside the storm structure, a pause created by the same system that is about to resume its assault with fresh force from the opposite side. The second half of a cyclone can be just as violent. People sometimes imagine that once the center has passed, the worst must be over. In reality, the returning wall of wind can be every bit as destructive as the first assault, and in some places, it feels worse because the landscape has already been weakened. Trees have lost branches. Roofs have loosened. Windows may be cracked. Then the storm comes back from the opposite direction and tests everything again. What survived the first round may fail in the second. This reversal is one of the cyclone's strangest signatures. The same storm arrives twice, with a short pause between, and the later blow lands on a place already rattled and exposed. For anyone standing inside that pattern, it can feel deeply unnatural, as if the weather has turned around and decided to attack again. That is why understanding the full structure matters so much. A cyclone is not one burst of violence. It is a rotating system that can strike, pause, and strike once more. Blue sky in the eye is one of weather's most dangerous deceptions. There are few sights more unnerving than sunlight appearing in the middle of a major storm. After hours of darkness, rain, and roaring wind, the sky can suddenly open into a circle of pale blue, as though the atmosphere has changed its mind. That moment feels reassuring to human instincts. Light suggests safety. Calm suggests survival. Yet in a cyclone, that clearing can be one of the most misleading scenes in all of weather. It invites people to step outside, inspect damage, or try to move to a new location just when they should still be sheltered. The danger lies in how convincing the illusion is. The storm has not ended. The violent ring surrounding the eye is still rotating, and the far side is already on its way. Blue sky becomes a trap precisely because it looks so harmless. In the architecture of a cyclone, beauty and danger can sit astonishingly close together. Storm shutters matter because wind-borne debris breaks homes before roofs begin failing. Wind alone is dangerous, but wind-carrying debris is far worse. Once branches, roof fragments, signs, or loose objects begin flying through the air, windows can shatter and doors can fail long before the main structure gives way. The moment that protective shell is broken, the house becomes much more vulnerable. Rain drives inside. Pressure changes rush through rooms. More openings form. Damage spreads from one breach into a chain of failures. That is why storm shutters matter so much. They are not a small accessory for cautious people. They are part of how a building keeps its integrity when the storm starts throwing the neighborhood back at itself. One intact window can help preserve the envelope. One broken one can begin a much larger problem. Cyclones reveal that homes are not only tested by what the wind does directly, they are tested by what the wind turns loose and hurls against them with terrible speed. Inland rivers can peak days after a cyclone, long after skies clear. One of the strangest things about cyclone flooding is how delayed it can feel. The storm clouds move on, the wind fades, and sunlight returns. Yet the rivers are still gathering the storm from far upstream. Rain that fell across hills, forests, farms, and towns begins working its way through the landscape, draining into creeks, then tributaries, then larger channels. The result can be a crest that arrives well after the dramatic part seems finished. A community may wake to blue skies and assume recovery can begin, only to find the main river still rising toward a peak that has not yet arrived. That delay changes how the disaster unfolds. The cyclone leaves, but its water keeps traveling through the land with patient force. It is a reminder that storms do not end when the clouds depart overhead. They end when the water they released has finally passed through every valley, bank, and floodplain in its path. Nighttime cyclones are especially dangerous because people cannot see the water rising. Darkness changes everything. During the day, people may spot flooded roads, waves crossing a seawall, or water creeping into a yard. At night, those visual warnings are stripped away. Rain, wind, and power outages can make the world almost unreadable, just when decisions matter most. A person may open a door and step into deeper water than expected. A driver may follow a familiar road straight into floodwater that was invisible until the headlights found it too late. Even inside homes, the sea or runoff can rise around people without the immediate visual alarm that daylight provides. That is why nighttime landfalls feel especially menacing. The cyclone is no less dangerous than before, but human perception. The storm keeps moving water, debris, and wind through the dark, while the people in its path must guess more and see less. In a flood, losing sight of the danger can become part of the danger itself. Evacuation orders are really race against water orders, not just warnings about wind. Many people picture evacuation as fleeing broken windows and fallen trees, yet the deeper logic is often about something heavier and less escapable. Water closes the clock. Once surge begins crossing roads or rivers rise into key routes, choices narrow fast. Cars stall. Bridges disappear. Escape becomes slower precisely when urgency is greatest. That is why officials issue evacuation orders before conditions seem unbearable. They are trying to move people before water takes away the map. In that sense, evacuation is a race, not merely against the storm's arrival, but against the moment when safe movement ends. Wind can be terrifying, but water traps. It isolates neighborhoods, cuts emergency access, and turns delay into entrapment. Understanding that changes how the order sounds. It is not simply a request to avoid discomfort or even damage. It is a warning that the landscape itself may soon become uncrossable, and once that happens, the storm decides where you stay. The safest response often depends on elevation more than distance from shore. People naturally think in terms of miles from the coast, as if danger fades evenly with every step inland. But in many cyclone disasters, height above water matters more than simple horizontal distance. A low area several miles from the shore may flood badly from surge, tidal rivers, or trapped runoff, while a higher location closer to the sea may remain far safer. The same principle applies inland along river valleys and floodplains. What matters is not only how near the water is, but whether the water can reach you once the storm begins reshaping the landscape. This makes topography one of the quiet keys to survival. A map of elevation can sometimes tell a more truthful story than a map of distance. Cyclones teach that danger travels through low ground. It follows channels, basins, and the easiest path inland. Safety, very often, is not about being far away. It is about being above the route the water wants to take. Cyclones reveal how small pressure changes can move oceans and remake landscapes. Pressure is invisible and usually ignored in daily life, yet inside a cyclone, slight differences across the atmosphere help set astonishing forces in motion. A drop in pressure draws air inward. Moving air drags on the sea surface. The sea rises, shifts, and surges into places it should not be. Beaches erode. Marshes drown in salt water. Sand is carved away from one place and piled into another. All of that begins with subtle changes in the weight of the air above us. Changes too small for the body to notice directly, yet powerful enough to help mobilize whole sections of coastline. That contrast is part of the cyclone's wonder. The atmosphere is not solid. It is thin, mobile, nearly invisible. And still, with the right organization, it can push on the ocean hard enough to redraw the edge of the land. Few lessons in nature are more humbling than that. Every cyclone is a physics lesson written in cloud, heat, water, and spin. Inside one storm, you can watch thermodynamics, fluid motion, pressure gradients, phase changes, and planetary rotation all working together at once. Warm water evaporates. Rising air cools. Vapor condenses and releases heat. Pressure falls. Air accelerates inward and curves under Earth's rotation. Water piles against coasts. Rain falls from towering clouds built by invisible energy exchanges. None of this is abstract when a cyclone is doing it across an ocean. The equations become visible. The planet turns theory into whether you can see from space. That is one reason these storms are so captivating even beyond their danger. They reveal that the world is governed by deep patterns, and those patterns can produce structures of startling beauty and immense power. A cyclone is not random chaos. It is organized physics, scaled up until cloud bands cover the sea and hidden laws of motion become legible in the sky itself. Few weather events show nature's power more completely than a full-grown cyclone. A mature cyclone gathers so many forces into one system that it feels almost like a summary of the planet's restless energy. It draws heat from the sea, turns Earth's spin into structure, lifts water into the sky, hurls that water back to the ground, drives the ocean inland, and alters the land it touches. It can be beautiful from orbit and devastating onshore. It can seem precise in its spiral form and overwhelming in its consequences. That combination is what makes it so unforgettable. Other weather events may be violent in one way or another, but a full-grown cyclone brings together wind, rain, flood, surge, motion, and scale in a single living system. It is weather as engine, architecture, and force of change all at once. To study one is to see how dynamic birth truly is. To witness one is to understand, in a very direct way, that the atmosphere is never still and the planet is never finished shaping itself. Of all the forces we have wandered through tonight, perhaps the most astonishing is how many worlds exist inside a single cyclone. We have traced the war motion that feeds it, the spiral shape shaped by Earth's turning, the strange calm of the eye, the towering clouds, the hidden structure, the flooding rivers, the shifting coastlines, and the long reach of these storms far beyond the shore. We have followed them across oceans, into history, into forests and wetlands, and even out toward other worlds where great spinning storms still turn beneath unfamiliar skies. And after all of that motion, all of that wind and water and power, there is something soothing in stepping back and seeing the whole picture. A cyclone is fierce, yes, but it is also patterned. It is part of the deep rhythm of a living planet, where heat rises, seas answer, clouds gather, and the sky begins to turn. So now, as this journey comes to a close, you can let the subject drift a little farther from you. Let the spinning bands move out over dark water. Let the rain soften into distance. Let the coast grow still again in your mind, and let your thoughts settle with it. And if you have enjoyed traveling through this remarkable world with me tonight, perhaps leave a like, subscribe to the channel, or share a thought below. And if you happen to still be awake, there will be another video waiting for you on screen, ready to carry you onward into another corner of science and wonder. But for now, there is nothing more you need to do. Simply rest. Let your breathing slow. Let your body grow heavy, and let the night hold you a little more fully. Sleep well, and good night.